Okay. Okay, so welcome to the ARCSIN seminar. It's a great pleasure today to have Ashish Mishra from the UFPA in Brazil, and he's going to talk about the Jucys Murphy elements. Ashish, please.
Okay. Good afternoon to everyone in India. Here it is morning. So, thanks to the organizers for giving me this opportunity to talk about the Jucys Murphy elements here. Okay. So let us start. So throughout the seminar, we consider our algebras are associative, and our algebras and also the representations are over the field of complex numbers C. Okay, so the Jucys Murphy elements were introduced by Jucys in 1971 and by Murphy in 1981 independently. So Jucys' paper was in an obscure journal, which was Lithuanian Journal of Physics, and many people did not notice that. And Murphy's paper later appeared in Journal of Algebra, which had a wider reach. So that's why the elements are associated with both of them. However, in Young's work, also these elements appear in one or another way. So that's why some people also call it Young Jucys Murphy elements. Okay. And the Jucys Murphy elements are defined in the following way. For the symmetric groups, of course, x1 is 0. And for I, from 2 till n, xi is this sum of transpositions. So it is an element of the group algebra of symmetric group. And this element is defined in the following way. Xi is 1i plus 2i plus 3i till I minus 1 comma I. Some of these transpositions, and one can see that this is the difference of sum of transpositions in Si and sum of transpositions in Si minus 1. Okay. For example, if you think about x3, this is 1, 3 plus 2, 3. And of course, it can be written as 1, 3 plus 2, 3 plus 1, 2 minus 1, 2. Okay. So, one interesting property of these xi's is that xi is an element of the centralizer of Si minus 1 in Si, of the group algebra of Si minus 1 in Si. Okay. What are the main results in Jucys' paper? An interesting statement which is there in the paper, which actually explains the philosophy of these elements. I mean, the statement is, if the basic function of the representation is at the same time a proper function of all the operators yk, its transformation properties under Sn are uniquely defined. Okay. When I read this statement for the first time, I did not understand what this statement was saying, because this is in this terminology is not in use in modern day mathematics. But after I thought, I guess that this probably means the following: that if an irreducible representation is okay, proper function here means eigenfunction, so it acts as scalars on these operators yk. He is denoting Jucys Murphy elements by yk. So if the Jucys Murphy elements act as scalars, then the representation of Sn, then that representation of Sn is uniquely defined by those scalars. And actually, this is the central philosophy of working with Jucys Murphy elements. Okay.
So, however, what does basic mean? Irreducible, is it?
I guess, I don't know. He says that he proved this in the last paper, which also appears in the same journal, but that paper is in Russian and I was not able to access that. So, but I find this statement quite interesting. For the reason that, I mean, this approach is, I mean, after the work of Okounkov and Vershik, it becomes more clear that these operators, I mean, these scalars actually parameterize the irreducible representation and their basis. Okay. However, he had already proved it in 1971. Okay. So the question is, what is the basic difference between then Jucys' work and the work of Okounkov and Vershik? The basic difference or the main difference is that Okounkov and Vershik start from the initial. They do not assume anything about the representation theory of SN, and they produce everything about the representation theory of SN working with these elements and Gelfand and Tsetlin algebra. Okay. However, Jucys is using the already known character theory or representation theory for showing that these scalars actually parameterize the irreducible representations of SN. Okay, so each element, I mean, there are two main results. I mean, we know that the center of a group algebra has the basis given by conjugacy class sums. And the main result in the paper is that each element in the center can be expressed as a symmetric polynomial or as a product of elementary symmetric polynomials in these elements x2 till xn. x2, xn are Jucys Murphy elements. Also, he gives the scalars by which these elements act and how to find these scalars from Young diagrams. That is by the content of the entries. For example, xi will act as, I mean, if V is the, I mean, Gelfand and Tsetlin basis, which we will define in some minutes, xiv will act as aiv, where ai is the content of the box with entry I in the corresponding Young diagram, okay, or Young tableau, standard Young tableau. Okay, standard Young tableau. So that is the thing. He gives these results. So what is the, I mean, what is the philosophy of working with these Jucys Murphy elements? The main motivation or idea comes from the work of Gelfand and Tsetlin in general linear Lie algebras. So, there is a combinatorial object which is known as Gelfand-Tsetlin tableau of height n, which parameterizes the irreducible representations of general linear Lie algebra GLN over the field of complex numbers. And basically, the Gelfand-Tsetlin subalgebra is a maximal commutative subalgebra of universal enveloping algebra of general linear Lie algebra, and that plays an important role there. And the idea is to generalize the idea of Okounkov and Vershik was to generalize that idea in the case of symmetric group. And in general, we can see this in the following way. Consider a multiplicity free chain of finite dimensional semisimple algebras. So, I mean, let me explain this. Okay, what does this mean? That this means that given a representation V of AH, it can be decomposed. I mean, since it is semi-simple and the restriction is multiplicity free, so this implies that this can be decomposed into a direct sum of irreducible representations of, let us say T, where Wi's are irreducible representations of AH minus 1. The word multiplicity free means that each irreducible representation of AH minus 1 appears here in the decomposition at most once. So either it does not appear, or if it appears only once. In that case, this decomposition is in terms of isotypical components, and isotypical components are canonical. Therefore, this decomposition into irreducible representations of AH minus 1 is also canonical. Okay. Furthermore, I mean, since we are considering the chain, the multiplicity free chain, so furthermore, if you restrict each of these WIs into furthermore, let us say UI J1, UI Ji, okay, and these are irreducible. This is decomposition in terms of irreducible representations of AH minus 2. This will also be multiplicity free decomposition, and this decomposition is also canonical. And if we go on doing this, you will finally get that V can be written as a direct sum of irreducible representation of A1, which is, or A0. I think we started with A0. So, which is only one dimensional. So finally, we get a canonical basis. We get a canonical basis of this V. We working with this multiplicity free chain. Okay. And such a basis is called Gelfand and Tsetlin basis. It is unique up to scalars. And also we know that we are in associative, we have associative semisimple algebras. So this AH can be written as a direct sum of matrix algebras over C. On the side of matrix algebras, we can consider a subalgebra which is diagonal, which consists of diagonal matrices. Okay, and that has an image inside AH. That image, that subalgebra is maximal commutative subalgebra, and it is known as Gelfand and Tsetlin subalgebra of AH, of this family. And the important point is that these Jucys Murphy elements actually generate these Gelfand and Tsetlin subalgebra, and therefore those scalars, the scalars by which Jucys Murphy elements act, parameterize the irreducible representations and their basis of Okay. So, and this is what is stated in this paragraph, that corresponding to this chain, we get a canonical basis called Gelfand and Tsetlin basis. And Jucys Murphy elements act as scalars, and they parameterize, these scalars parameterize the irreducible representations and their basis. Furthermore, so basically what are the fundamental properties and advantages of Jucys Murphy elements? There is no algorithm to determine Jucys Murphy elements in various cases. However, we call elements as Jucys Murphy elements when they satisfy these fundamental properties. First of all, these Jucys Murphy elements commute with each other. And one shows that the irreducible representations of AH and their bases are determined by the actions of these elements. And the sum of all Jucys Murphy elements of AH is a central element of H. For example, in the Sn case, if you add all x1, x2, xn, these Jucys Murphy elements, it is the sum of all transpositions, which is a conjugacy class sum, so it is a central element. What is the advantage? Advantage is that one considers the representation theory of the whole family rather than an individual object. And usually one gets a combinatorial object parameterizing the irreducible representations and their basis. And the advantage is also in terms of some new applications which arise. For example, in the PhD thesis of Shubhajit Ghosh, student of Arvind Iyer, he worked with the spectrum of transition probability matrix for the random shuffle of G-Reth Sn, where he used the Jucys Murphy elements of G with SN. Okay. And also there are other applications like in my PhD thesis, I mean, we worked out the decomposition of generalized Johnson scheme in terms of irreducible representations of G with Sn. Okay.
Sorry, can I?
Yeah.
Sorry.
So I wanted to ask that V that you said, it's GLV, that V we were using to define H.
V.
This
V is an irreducible representation of H. AH. V of AH.
So
AH is a, yeah.
You want this to be for all. Oh, okay, I see. That's why it's multiplicity free. Because is it?
Sorry.
Sorry. So is it multiplicity free? Multiplicity free because it's irreducible.
No. We are already assuming that it is multiplicity free.
Okay.
So every irreducible representation of AH will decompose in a multiplicity free way. I mean.
Okay. So for all V.
Representations of AH minus 1. Yeah, for all V. For any irreducible representation.
Okay. Thanks.
That is what we mean by saying that it is a multiplicity free chain. Okay, so that at each step it is multiplicity free for all irreducible representations. Okay.
I just wanted to
yeah.
So this you gave this characterization of Jucys Murphy element, not characterization in the last slide which we were talking about.
Yeah, this.
Yeah, fundamental property. So now this has no reference to the chain of algebras. You just have one algebra. However, and that is how Murphy and Jucys actually introduced these elements. They didn't talk about the chain of algebras. However, I think now we would actually, when we talk about Jucys Murphy elements, we would be requiring also that the nth Jucys Murphy element generates the algebra corresponding to AH, and the previous ones generate the algebra corresponding to AH minus 1, right? I mean,
yeah.
And that may almost uniquely determine the, up to some, modulo the previous ones, each one is uniquely determined in some sense. Modulo the.
Yeah. Yeah, and when Jucys and Murphy considered, at least when Jucys defined it, he was not considering the chain. Okay, so the chain idea is basically generalization by Okounkov and Vershik.
So my question is about the uniqueness. Is that correct? What my guess is that they are essentially unique if you have support.
Yeah, they should be unique because these scalars are parameterizing. Yeah, so in a way,
Anyway,
yeah. Okay.
Sorry, I just had a question. So
yeah.
you were saying about Jucys Murphy element for G with SN. So you don't need the branching to be multiplicity free to get this.
Yeah, so that is the interesting part, that actually this which I was coming in the next slide. You see this product of finite groups by symmetric groups. In this case, the Jucys Murphy elements was given by Pushkarev in 1999, and he does not have a multiplicity free chain there. So what has happened there in his paper is that somehow the theorems are correct, but the way he has proved it, at least the main theorem, one or two main theorems, their proofs are incorrect because he does not have a multiplicity free chain there. Okay, so what in my PhD thesis, we produce this for this G-Reth Sn, we produce a multiplicity free chain. Of course, this G-Reth Sn containing G-Reth Sn minus 1, this is multiplicity free if and only if G is an abelian group. G is a finite abelian group. Okay. For any arbitrary finite group, this is of course not multiplicity free, and we produce a multiplicity free chain so that so that we can work with this idea.
Okay, so you always need multiplicity freeness to get Jucys Murphy element.
Yes, I mean, ideally that should be true because you need a canonical basis.
What do you mean produce? Do you add more terms in between or something?
Yeah, so like, I mean, in this case, when we started here, I mean, if we consider for the symmetric group case, we consider this chain, yeah. Sn, and this is just identity. But we do not put the restriction that the base group here is an identity group, is just identity element. So you just work with this. I mean, G-Reth Sn is this semi-direct product, yeah. So basically, you show that this and so on till Gn. Now, this base group may not be identity, but that is okay because then you will get Gelfand and Tsetlin subspace. But this is a multiplicity free chain.
So Sn minus
So
1
basically,
acts only on the first n minus 1.
Yeah, that I did not say. So Sn minus 1 is contained inside Sn in such a way that it fixes n. So Sn minus 1 acts on the first n minus 1 components and fixes the last component of Gn.
So instead of working with that chain, you work with this.
Yeah. And modulo this, I mean, so of course, this G is not identity here. G may not be identity here. So you will not get a canonical Gelfand and Tsetlin basis, but you will get a canonical Gelfand and Tsetlin subspace. And the action of Jucys Murphy elements of G-Reth Sn parameterize those irreducible representations. I mean, that is the main result.
Would it have been possible to just refine this chain to get something? I mean, now you've changed the chain, but
yeah.
Could you refine?
You mean?
I guess there must be obvious examples where you have a group and a subgroup, and you cannot find the chain in between where the restrictions are multiplicity free.
Okay.
Kind of interesting to see when you can find such chains.
Yeah, that is an interesting question.
Yeah, it just occurred to me. It seems intriguing. Maybe.
Yeah, but I mean, probably, I mean, Soham was working with this thing in his PhD thesis, and probably for solvable groups, it should be true. I mean, that you should be able to find the chain of maximal subgroups inside the solvable group.
Those have multiplicity free always? You saying if the quotient is
For nilpotent groups, I think maximal subgroups are index P. So that is true. But yeah, solvable, I don't know.
Okay. Mm-hmm. Yeah. Yeah, that is an interesting question, but okay. So let us.
Sounds like a interesting question.
Yeah. So, okay, so I mean, these are some families of groups which are groups and algebras which I have mentioned here, but there are more families of algebras for this, for which Jucys Murphy elements have been found out. I mean, so I will mention a few. Symmetric groups was, of course, by Jucys and Murphy. The product of finite groups by symmetric groups was by Pushkarev. For partition algebras, it was done by Halvorsen and Ram in 2005. For Q-root monoid algebras, where Q is not equal to 1, was done by Halvorsen in 2004. For partition algebras, for complex reflection groups, it was done by myself and Shraddha Srivastava. And for rook monoid algebras and partition algebras for rook monoid algebras, also this was done by both of us. And later on, for generalized rook monoid algebras, it was done by Mazurchuk and Shraddha. Okay,
what about alternating groups? Has anyone done it?
Yeah, I did not mention it. Oliver Ruff has done it for alternating groups.
Oh yeah, I knew that.
Yeah.
No.
Okay. So yeah. So I mean, in the abstract, I had mentioned all these cases for Jucys Murphy elements that we will probably cover these, but later on when I was making slides, I thought that I was being too greedy and it would not be possible. So for the talk, I have just concentrated on this partition algebras for complex reflection groups. So let us see complex reflection groups. For us, R, P, M, and N are positive integers such that P divides R and M is R divided by P. Also, we consider zeta to be a generator of cyclic group of order R. And then we define DRPN to be the subgroup of GLNC consisting of these diagonal matrices such that the sum of the exponents is 0 modulo P, or one can say that this product and raised to power M, where M is R divided by P, this should be 1. The product of these diagonal elements and their power. Okay, so this Sn acts in a natural way on these diagonal matrices, and this gives rise to a semi-direct product where this G, which is denoted by GRPN. GRPN is DRPN semi-direct product by Sn, and for P is equal to 1, when P is equal to 1. This is actually what we call as Reith product of cyclic group by a symmetric group. Okay. Equivalently, one can consider this GRPN to be a group of n plus 1 tuples where the exponents, I mean, this is the same condition that the sum of the exponents is congruent to 0 modulo P. Sorry. Okay. And pi is an element of Sn. Okay. Now, according to, so this GRPN is, except the case when RPN is the tuple 2, 2, 2, this GRPN is an irreducible complex reflection group. I mean, it is a complex reflection group even in the case when RPN is 2, 2, 2, but it is not irreducible in that case. So this family, GRPN, is the only infinite family of irreducible finite complex reflection groups. And in the classification, there are 37 families. 2 families are included within this. 2 more families are included within this GRPN, which is, if you consider R and P to be 1, then this GRPN is symmetric group Sn. And if you consider P to be 1 and N to be 1, then GR11 is the cyclic group of order R. And there are 34 other, those are not families, but those are some exceptional cases which are actually primitive complex reflection groups. Okay, for working out with the theory, we need an analog of Sn-1 inside, I mean, like the role which Sn-1 plays inside Sn, we need an analogous subgroup of GRPN. And we notice that this happens to be that subgroup which will play a significant role here. LRPN is DRPN semi-direct product by Sn-1, where Sn-1 is fixing the last component. And one can see that by a short exact sequence that GRPN and LRPN are normal subgroups of the group GR1N and LR1N. Both are of index P. And these are some special cases which arise in some special families which are subcases of GRPN. These two we have already discussed, and this dihedral group of order 2R appears when P is equal to R and N is equal to 2, and while group of type Bn and while group of type Dn are also complex reflection groups of the form GFP. So our aim is to define Jucys Murphy elements for the partition algebra of complex reflection groups. For that, of course, we first need to define partition algebra for complex reflection groups. And even before that, we need to consider representation theory of complex reflection groups. And this is as follows. So we know that for GR1n, or for Reith product of any finite group G by symmetric group Sn, where G has R conjugacy classes, the irreducible representations of GR1n are parameterized by R tuple of Young diagrams with total number of boxes equal to n. So we know that this is a normal subgroup of index P. And actually, this quotient group is a cyclic group of order P. We will use Clifford theory to study representation theory of GRPN from the representation theory of GR1n. This was, the earliest I have seen it is in Stembridge's paper. Okay. So let us see. For that we need first MP necklaces. What is an MP necklace? Consider this tuple λ1 till λ2 λr. Start with λ1 and make a jump of m places. λ1, λm plus 1, and so on. So this, and do this for each I between 1 till m. So for each I between 1 to m, you will get a necklace of this form. Okay. This has P nodes. And what is an MP necklace? An MP necklace is an M tuple of these necklaces. Lambda tilde 1, lambda tilde 2, lambda tilde n. What will be lambda tilde ij? Lambda tilde ij means that, we are considering it here. So lambda tilde ij means that jth node in the ith necklace. Okay. Let me write it down. So lambda tilde ij means jth node in ith necklace, ith component. Okay. So in Clifford theory, what we do is if n is a normal subgroup of H, we consider. This is a specific case of Clifford theory where we can make more deductions, because here the quotient group is a cyclic group So we are in that case, n is a normal subgroup of H. We consider those one-dimensional representations of H which contain n in the kernel, and this group acts on the irreducible representations of H. And furthermore, using Clifford theory on that, we see that the irreducible representations of the complex reflection groups GRPN are parameterized by MP necklaces. In that action, we have some stabilizer subgroup also, which is a subgroup of ZP. And this stabilizer subgroup, if we want to see an example, let us consider this. Only we consider an easy example. Let us consider this tuple 2, 1, 2, 1, and so here R is 4. Let us consider P to be 2, and N is here 6. So in that case, we will get this. This 2 tuple of necklaces, and no, this will be 2, 2, and 1. because we are making a jump of 2. So the stabilizer subgroup here will be equal to Z2, because when we rotate each necklace, we get back the same necklace. Okay. So here the stabilizer subgroup is actually equal to Z2, but there will be cases where it is a proper subgroup of ZP. And in many cases, usually the stabilizer subgroup will be, in most of the cases, it will occur that the stabilizer subgroup is just identity. Okay. So what are equivalent MP necklaces? Two MP necklaces are equivalent if if you can rotate all the necklaces in the same way to get the other necklace. Okay. So I mean, under the action, I mean, when this for example, okay, we consider another example. So this gives rise to this necklace. Just to consider that this is actually equivalent to this. And this is actually obtained from by Clifford theory, we can see that this irreducible representation and the irreducible representation parameterized by this tuple and parameterized by this tuple actually restrict to the same irreducible representation of GRP. Okay, that's why we are using the MP necklaces, because these two are equivalent when you are thinking about irreducible representations of GRP. And by Stembridge's result, these the irreducible representations of GRP are parameterized by the order tuples. Lambda tilde is the necklace, and delta is the stabilizer. Delta is an element of the stabilizer. Okay. So how much more time do I have? It is already 7:38. Sorry.
Yeah, you have 20 minutes, but don't stress out too much here.
Okay. So, okay. So, yeah. Okay, so we have this Sn-1 is a subgroup of Sn. It consists of all those elements which fixes n, and representation theory is that if V lambda from Sn to Sn-1 is that it is a direct sum of all V mu, where mu is obtained by deleting an outer corner from the Young diagram lambda. Okay. Now we have this subgroup LRPN inside GRPN, and we need the multiplicity. I mean, we need the decomposition rule of irreducible representations of GRPN in terms of LRP, in terms of irreducible representations of LRPN. For that, we will be using colored MP necklaces. So given this MP, YMPN -1 denotes MP necklaces with total number of boxes n -1. The Nij colored MP necklace denotes the necklace which is obtained by coloring this mu tilde ij by n, which means that, I mean, jth node of ith necklace should be colored by n. And the two colored MP necklaces are equivalent if one can obtain one from the other by rotation, by the simultaneous rotation of all the necklaces. And this is a result which we proved in our paper. I mean, this was an easy result, and the proof is analogous to the proof for the case of irreducible GRPN modules. The irreducible LRPN modules are parameterized by Y and MPN minus 1, which is the set of all inequivalent Nij colored MP necklaces of total n minus 1 boxes. Okay. So with these two results, I mean, the main result here is branching rule from GRPN to LRPN. And this is, I mean, in the partition algebra case, I mean, whenever you have Schur-Weyl duality, or to find the Schur-Weyl dual of a given algebra, there is problem on both sides. So here, the problem was to finding this branching rule from GRPN to LRPN, and this is one of the most important results in the paper, that given lambda tilde an MP necklace, this lambda tilde down arrow ij denote the set of all elements in Nij colored MP necklaces obtained by deleting a box from an inner corner in the jth node of ith necklace and then coloring the node by n. And to ensure that the same equivalent or the equivalent Nij colored MP necklaces do not appear more than once, we define this Ji. It is the set of all elements in one T, such that for S and T in Ji S not equal to T, this lambda tilde down arrow Is, lambda tilde down arrow It have empty intersection. It can be seen that if they do not have empty intersection, then this is equal. Okay, so we want to consider only those elements in Ji for which this intersection is empty. And this is the branching rule from GRPN to LRPN. Given this lambda tilde delta, which parameterizes an irreducible representation of GRPN, those irreducible representations of LRPN appear, which are parameterized by Nij colored MP necklaces, such that this J belongs to Ji and I varies from 1 to n. And of course, this branching rule is multiplicity free. Idea of the proof is that, I mean, first one has to construct this construct the basis of irreducible GRPN modules by using higher respect polynomials. Then one says that if you consider the same lambda tilde and delta 1, delta 2 belonging to the stabilizer subgroup of lambda, then these two irreducible representations of GRPN, their restriction are equivalent as irreducible representations of LRPN. And finally, we use transitivity of restriction from GR1n to LRPN by the following two chains, okay, GR1n to LR1n till LRPN and GR1n to GRPN till LRPN. So this will give, this finally gives the branching rule. Now coming to partition algebras. Okay. Okay, so I hope I don't know whether I will be able to finish in 15 minutes. Let us see. Partition monoids. So partition algebras were defined independently by Jones and Martin in the early 1990s. Okay, they were defined as a general. I mean, Jones defined it as a generalization of a Potts model in higher dimensional statistical mechanics. So for defining partition algebra, let us first define what is a partition monoid. For partition monoid, consider k any non-negative integer, and consider AK to be the set of all set partitions of 1 till k, 1 prime till k prime. And we depict these elements as partition diagrams. For example, if you consider, for example, let us consider this D1. This is a partition. Okay. So this is a partition of the set with elements 1 till 4 and 1 prime till 4 prime. And these are the blocks. 1, 1 to 1 prime, 3, 3 prime, 4 and 2 prime, 4 prime. The blocks are connected by edges, and this is the way elements of AK can be depicted as partition diagrams. AK is a monoid with multiplication. The multiplication can be done by the concatenating the partition diagrams. For example, in this case, D1 and D2, in these two diagrams, the concatenation is done in the following way. 1, 2 goes to 1 prime, and 1 prime is identified with 1. 1 goes to 2 prime, 3 prime. So this is one block, 1, 2, 2 prime, 3 prime. Here there is a block 3, 3 prime. 3 prime is identified with 3, and then 3 does not go anywhere in the bottom row of D2. So 3 here is a single block, is a singleton block. 4 is a single block in the top row of D1, so it remains that way. Whatever is in the middle will remain in the middle here. Like 2 prime, 4 prime is identified with 2, 4, but they do not go anywhere in the bottom arrow of D2 or in the top in the bottom row of D2 or in the top row of D1. So that's why, I mean, we do not consider this whatever is in the middle row. And now consider the bottom row of D2. 1 prime is identified with 4 prime, but they are not connected to anything in the top row of D2. So that's why this is a block in D1 composed with D2. This is the way to multiply D1 and D2. And with this multiplication, AK is a monoid. We consider a submonoid of AK or AK plus 1 in the following way. That okay. So for this is 1 till k, 1 prime till k prime. So or k plus 1, k plus 1 prime. So I mean, AK plus half is the set of all elements in AK plus 1, such that k plus 1 and k plus 1 prime are always connected in those elements. Okay. So this is what we mean by AK plus half. And one can see that this AK and AK plus half are monoids, and these are called partition monoids. So partition algebra is is given by for any complex number q. CAKQ is the C span of these partition diagrams. And this is an algebra using the product which is given by the product of in partition monoids. So CAK plus half q is, and in a similar way, CAK plus half q can be considered to be a subalgebra of CAK plus 1q. What happens here is that multiplication D1, D2 is q raised to power L, D1 circle D2, where L is the number of blocks which are entirely in the middle in the product D1 composed with D2. For example, here, I mean, if we are considering D1, D2 as element of partition algebras, then this product will be q raised to power 1 D1 circle D2. Because there is only one block which is entirely in the middle in the product. Now, sure-while duality. First, Jones gave this sure-while duality between Sn and the partition algebra CAKN while they act on V tensor K, where V is an n-dimensional complex vector space. And later on, Martin and Rowlett gave this sure-while duality between Sn minus 1 and partition algebra CAK plus half n, while they act on V tensor K. This, considering this Sn minus 1 inside Sn is useful because then you get a multiplicity free chain of partition algebras. This chain CA1 and inside CA and so on. This chain is not multiplicity free. However, when you introduce these half partition algebras, these become multiplicity free. So this is the explanation of Schur-Weil duality, which I will skip for now and come to the partition algebra for complex reflection groups. Tanabe had considered in 1997 the centralizer algebra of this complex reflection group GMPM, and Orellana in 2007 had defined, the title of the paper is on partition algebras for complex reflection groups. However, what she had done was that she had defined partition algebra just for GR1n. Of course, what the partition algebra, the way she has defined partition algebra does not work in the same way for GRPM. Okay. And also in the results like in the case of SN in the case of partition algebra for symmetric groups, you are considering SN-1 inside Sn to get that multiplicity free chain. In a similar way, you have to consider a specific subgroup here, which we are denoting by LRPN, to obtain this Bernoulli diagram for the chain of partition algebras for complex reflection groups. So what we did is the following. The main results in the paper are as follows. The paper is titled on representation theory of partition algebras for complex reflection groups. And the first main result is to define partition algebra for complex reflection group in general. Okay, where P is any divisor of R. And in honor of Tanabe, we call these algebras as Tanabe algebras. So the first main result is definition of these partition algebras. The second main result is to establish Schur-Weil duality between TK-RPN and GRPN, and between TK plus half RPN and LRPN while they act on V tensor K, where V is reflection representation of complex reflection group. Okay. This result I had already explained while we were discussing complex reflection groups, that construction of a basis of irreducible GRPN modules using a confluence of ideas from Okounkov-Vershik approach, Clifford theory, and higher spec polynomials, and its application to determine the branching rule. And using Schur-Weil duality, one can, to use Schur-Weil duality, one has to first decompose this V tensor K and V tensor K plus half. This V tensor K plus half is actually this V tensor K. It's a product Vn, where Vn is the nth. One can consider. This V is an n-dimensional complex vector space. So this Vn we consider as nth basis element. So this decomposition of these two spaces in terms of irreducible GRPN and LRPN modules is an important result here because you need this to work with Schur-Weil duality. To use Schur-Weil duality, it is important here that we use Okounkov-Vershik approach again. What some of the results which Orellana was using in her paper are insufficient here, and also those results are hard to prove. Those results use Rim-Hook tableau, but using Okounkov-Vershik approach, the proofs are this. First of all, one can obtain this result, and the proof is much easier. Okay. And then parametrization of the irreducible modules of Tanabe algebras. Here one has to use Schur-Weil duality and this result. Later on, we construct Bernoulli diagram. And to construct Bernoulli diagram, one needs this result. Branching rule here. Finally, there is description of Jucys Murphy elements of Tanabe algebras and their actions on a canonical basis called Gelfand and Tsetlin basis of each irreducible module of Tanabe algebras. Okay, these are the main results which were there, and the focus of this talk is Jucys Murphy elements. So what I have done is I have made two appendices, one with this definition and another with the description of Jucys Murphy elements. Okay, so if there is interest, I can describe how to define these Tanabe algebras, and later on I can describe these Jucys Murphy elements also. So this is the main part of the talk, which is over, but I had made two appendices. That's what I am explaining. So based on our time, we can do that.
Yeah, sure. Okay, go ahead. Maybe some people may have other appointments they may leave. But,
Oh, and if there are some questions, I mean,
yeah, sure.
specifically.
Maybe we can.
Yeah.
So if you want, you can just unmute your mic and ask the questions.
Ashish, very good talk. That is a very good talk. Now I have one little point. When you took
Yeah.
the element which was 1 on all the elements in SI except SI minus 1, that means this is a element of group ring which is constant on the double coset of SI minus 1 in SI. But when you multiply this with itself, then the function constant on SI minus 1 also enters, and function constant on this double coset also enters. And the constants are 1 by I minus 1 and I minus 2 over I minus 1. And that means the two elements generate a two-dimensional group ring, you know. And this comes under the discussion on double coset hypergroups algebras. And,
Okay.
and this was explained by Dunkel in an old paper, and the title of that is Krachuk polynomials, but it is put as a remark there in the last page. So when you take these functions constant on double cosets, then you get only a two-dimensional hypergroup algebra, constant on the two double cosets, you know. And now what my question would be, if you take other groups and then subgroups, then when you take double coset subgroups, what is the situation?
Okay.
I'm not wanting you to answer right now. My idea is
Yeah.
to make you aware of this.
Okay. Yeah, I will think about it, and I will talk to you about it
Sure,
later
sure.
through email also. Yeah.
Okay, wonderful
Because
talk. Thank you.
I'm not aware of this.
Yes, yes.
But yeah. Okay.
Thank you.
Yeah, thank you.
And you know, then representations, tensor products of irreducible representations is a sum of irreducible representations. It is not an irreducible representation. So all that also comes under the study of hypergroup algebras.
Okay. Yeah, that is probably Gordon-Clapp's problem. Yeah. To find the decomposition of tensor product in terms of irreducible representations.
So of course, yeah, that's the Kronecker problem for symmetric groups, which is quite hard. That two-dimensional algebra plays a role in Okounkov and Vershik's paper.
Yeah, that is degenerate affine Hecke algebra H2N, which plays an important role here.
So is there an analog
probably
of that?
Is it same as the hypergroup algebra which Professor Ajit Iqbal Singh was describing.
So it's the Hecke algebra
But that,
of Sn against Sn minus 1. That is a
Yeah.
Gelfand pair.
yeah,
But when you multiply that function which is constant on the second double quotient, that means Si minus 1 as he put it, then the product will contain a part which will be constant on Si minus 1 considered as a part of Si, and another part which is constant on the other double quotient which he called as Si minus 1.
okay.
You see, I mean, as the element stands, Si minus 1 does not appear. But when you take the group ring product convolution, I mean to say, then it will appear.
Yeah.
Okay. Mhm. Yeah.
Sorry, so I just wanted to
Yeah.
I just
Yeah,
wanted to
Sridhar.
come back to read thing again. So suppose you have G
Yeah.
Tensor, and if G has Jucys Murphy's element, then is there like a read action to get the Jucys Murphy's elements of the read product?
So I mean, the Jucys Murphy elements of G Sn are known, yeah, but the elements of G play a role, but I mean the Jucys Murphy elements of G do not come into picture there, yeah.
Okay.
Those were given by Pushkari.
So when you say the Jucys Murphy elements, I mean,
Yeah.
for
So
what
that
groups do
question
these
about
even
uniqueness.
exist? Right?
Sorry?
You want so basically abstractly you have a group, then you have its group algebra, then you take its center, and then you want okay. So now what is this? I mean, as far as I can see, there's no Gelfand Tsetlin algebra unless there's a chain of groups, right?
Yeah, unless
But-
there is a chain of groups.
But
Yeah.
Jucys and Murphy still defined these elements before they thought of it. Apparently, I mean, maybe without seriously thinking about the chain of groups. So they
Okay,
must
so,
have
yeah.
thought about it in some sense, but maybe not so explicitly.
Yeah, probably. Mhm.
So I'm just trying to understand what is the meaning of. Okay, so you gave those 3 points, I guess. So that's about all you can.
Yeah, and so there are results for Hecke algebras also, these Jucys Murphy elements. And okay, so there is some comment in the chat. From broad to narrow. Okay, but first of all, you have to, you have to have some, regarding the comment in the chat, you need to have some background in representation theory also. And then there are various types of algebras for which you can work with Jucys Murphy elements. And also there are applications in probability theory and other parts of mathematics.
So coming to the probability theory, already I think Backponis and Shah Sahani use these things, right?
Yeah, for SN.
Yeah.
And for G SN, it was done by Shubhajit.
Yeah. So there, I remember, I think there's some estimate in that workshop that are organized.
Yeah. And this uniqueness thing, okay.
So, but already if you take the center of the
Yeah.
group algebra, that's much smaller, right?
Yeah,
And
that's much smaller.
but the characters of that, I mean, if you look at an irreducible representation, if you just you know that if you know how the center acts, then you know the representation. So it's already determined by that. Right. So,
Yeah, but I mean, these Jucys Murphy elements are not central elements. Yeah, that is.
yeah. So again, without the tower of algebras, I don't understand how to.
Yeah, without the tower of algebras, of course. I mean, so that's why I mean these.
But I guess yeah.
And of
There's
course, I
another
mean,
question.
like, yeah. First you ask and then I will say. Yeah, first you say something and then I interrupted you, so you can.
No, there's another question in the chat which I don't quite understand. Yeah.
Sorry. There is a, I mean, I can see only 4 messages. Let me.
How does it? Okay, so there's a question. Oh, it's only sent to me. How does so Hamoud asks how the complex reflection groups on the abelian group looks like. But
Sorry, how the complex reflection groups?
for the abelian group, I'm not sure I understand this question. Anyway, leave it.
Yeah.
So the definition of the complex reflection group was given in your slides.
Yeah.
It's very specific.
I mean,
3 parameters.
Yeah.
And, yeah.
Yeah, I mean, this was for a specific complex reflection group GRPN, but if you want to define a complex reflection group in general, it is generated by reflections or pseudo reflections. And pseudo reflection is a linear isomorphism on an n-dimensional vector space, which fixes a hyperplane. And this linear isomorphism is of finite order.
What is a good reference for those who want to start learning about complex reflection groups? Like just basic things up to classification.
Okay, so the whole classification right from the definition is done in Sheffer-Todd, which is, I think, a bit difficult, but Cohen wrote a paper based on that theory in 1959, which I think is easier.
But it's not in the textbook or something?
Okay, so we studied right from the paper, but there must be textbooks, yeah. So, yeah.
So Cohen's paper.
Yeah, Cohen's paper is better. And the paper is easy if you know the basics of representation theory. So it's not difficult, at least at the starting.
So it's AM Cohen finite complex reflection.
Yeah.
Just share the thing in the chat for those who are interested.
Okay.
Archie Cohen.
And also, I mean, this complex, there is this relation with invariant theory. That invariant theory of, invariant ring of this finite group on a complex vector space is a polynomial ring if and only if it is a complex reflection group. So that is Sheffer-Todd theory. Yes, I mean, that uniqueness question which you asked.
And actually, I think in one of either Vershik's papers or Keroff, maybe they talk about this thing in the sort of more abstract setting, chains of semisimple algebras with multiplicity free.
Okay.
I don't remember now exactly what.
Okay. And then this, yeah, and it is not, I mean, it is not necessary that if you have a chain of n, let us say that you have this chain of algebras A1 contained inside A2 contained inside AN, which is multiplicity free. So it is not necessary that you will have only n Jucys Murphy elements. Like in the case of root monoid algebras, you need more to classify or to parameterize the irreducible representations.
Which algebra?
Root monoid algebras
Group monoid. You need more.
or totally propagating partition algebras, or even in this partition algebras for complex reflection groups. I mean, so these we have most of the Jucys Murphy elements we had already got when we were working on this paper. But there was one case which was exceptional case, which is RPN is 2K. Okay. And for that, there is only one Jucys Murphy elements, but for that case, you actually need an extra Jucys Murphy element. So sometimes it also depends on these parameters RP and N. For some parameters, you may need less Jucys Murphy elements, and for some other parameters, you may need more Jucys Murphy elements to actually distinguish the irreducible representations.
Are there any more questions? Looks like there are no more questions. So let's thank Ashish.
Okay, thank you.
Thank you, and thank you also for accommodating my request for a change of schedule.
No, it's okay. So this is okay. So the semester actually begins after 10 days. So